Hi everyone, can you hear me? Yes?
Yes, yes.
You can hear me, no? Alright guys, let's start. We waited for 10 minutes for everyone to join, but unfortunately people have not joined. Doesn't matter, we have to start, right? So today we are doing the chapter number 4, right? Yesterday we did chapter number 1. So chapter number 2 and 3 are recorded. I have not uploaded the lecture yet. I'll upload it tonight or tomorrow. So you can watch them in your spare time. Long chapters, it will take some little more time, so you can go and watch it. But let's talk about chapter number 4, right, which is backtesting of VaR, which is very independent kind of chapter with the from the previous chapters, right? So backtesting of VaR is very very important, guys. Backtesting is in fact one of the Basel requirement also, right? So this chapter we are focusing on obviously the fourth chapter of your market risk. The module is all about your testing whether your value at risk model, right, actually works or not. Why do we do back testing, right? Back testing is all about to test whether your particular model which you have selected, does that work or not? Does it actually correctly predict the probability of losses which are exceeding VaR or not? That's the whole objective, guys. That's it, right? That's the objective of the chapter. We'll try to understand that. Okay, let's dig deeper and take it further. Okay, so now this module, right? This module is further subdivided into your 7 parts, right? So we'll focus here on first of all backtesting VaR models. We'll talk about why backtesting kind of matters, right? When you build a VaR model, you assume or you estimate the maximum expected loss at a certain confidence level, let's say 99%. But how do you know if the model is kind of accurate, right? And the way to find if it is accurate or not is to test it against your results. That's called your backtesting, right? The structure of the module is the section is divided into the 2 modules, right? If you go back, right, there are 2 modules which we have here. Module 1 is your backtesting VaR models, which will cover your uh, concepts I'll discuss ahead, and then second is your conditional coverage and your Basel backtesting rule, right? So in your module 1, right, module 1 is all about your basic of backtestings and exceptions. What are exceptions, how they indicate your model accuracy, difficulties in backtesting, why results may not perfectly match your reality, what are the difficulties in backtesting, what are the failure rates, how often losses exceed your VaR, what is the model verification example, a big example to show how to test, what are the type 1 and type 2 errors, statistical mistake in rejecting or accepting a model, type 1 and type 2 error you have seen in FRM part 1, right? Then the unconditional coverage. When I say unconditional coverage test, means you check whether number of exceptions matches the expectation. Exceptions matches the expectations, right? We'll see it at no, don't worry. And then we have your measuring of your potential losses. When I say measuring of potential losses, it means how VaR helps you to quantify your possible downside risk, right? Module 2, right, which is not discussed here, but module 2 is more about conditional coverage and Basel backtesting rule. What is conditional coverage? Conditional coverage is you are testing if exceptions are randomly spread or you are testing if exceptions are clustered. Why do we need to have this understanding of randomly spread or clustered? Because this is very important when you're trying to understand your time independence or time dependence. And then you have something called your Basel backtesting rule, which will have your Basel traffic light approach. What is the traffic light approach? The regulatory method, which is used by your banks to evaluate your model performance based on some exception count, right? We'll see that. Don't worry. Okay. So I have see the objective of speaking so much in the initial part is that I want to give you a good overview of what we are going to do now, right? So we are going to understand backtesting. We are going to understand exception. We will try to understand what exactly is a good model. We will try to understand unconditional coverage. We will unconditional coverage means we'll focus on your number of exceptions. We'll look at the conditional coverage, right, which will focus on the pattern of exceptions, whether they are independent or independent. That will go in module 2. And then we'll focus on the Basel rule, where we'll talk about what exactly the regulator does, right? Regulator classify the models into green, yellow and red zones based on your exception. Another point now comes is that why are we studying it, right? Why are we studying it in FRM part 2? See, we are studying it in FRM part 2, right? Please understand, because regulators such as your Basel committee require banks to backtest their VaR models daily. Remember that, daily. You have to backtest your VaR models daily as per the regulatory requirement. It tests your both model accuracy as well as model stability. So two things again, accuracy and stability, right? So you need to understand the exceptions, you need to understand the coverage, you need to understand the test, you need to understand the Basel traffic light thresholds. So there is a lot of understanding that you need to develop here. Okay, so let's try to now dig deeper. Okay, take one thing at a time. All right, the first understanding here is your backtesting and exceptions. What is backtesting, right? See, backtesting means comparing your VaR models predictions. Okay, obviously you have a VaR model that will predict your losses. You will have some VaR models prediction. You will compare those VaR models predictions with your actual realized losses. Why? Why are you doing this? Why are you comparing your VaR models prediction with your actual realized losses? The logic is that you want to check whether the model is accurate or not. Okay. In other words, I can say I want to understand, did the model really behave the way it was predicted? It's the model validation process used by two parties, one by your risk managers, other by your regulators, right? The Basel committee. Okay. The overall goal here is to ensure that the actual losses do not exceed the VaR more frequently than expected. You can exceed the VaR sometimes, right? Minor few times, one, two, three, right? But you should not exceed it more frequently than the expectations. So let's say if you see or if you use a 99% confidence VaR, you expect losses to exceed VaR only 1% of the time, right? That is about, what is 1% of your 250 days, right? It is 2 to 3 days, right? 250 trading days, right? So that is what the whole idea is. Now the question comes is, what are expectations or exceedances, right? Expectations and exceedances are the days when actual losses are greater than what was expected, right? When I talk about exceptions and your exceedances, right, these are days when actual losses are greater than the predicted VaR. So let's say we have 99% VaR. I told you 99% VaR. Expected expectation is what? 1%. 1% in 250 trading days is 2 to 3 days in 250 trading days. If you have 95% VaR, expected exceptions are 5%. When I say 5%, 5% of 250 days are what? 12 to 13 days in 250 days, right? So if your model is perfect, if your model is good, actual exceptions should match these expectations. Too many exceptions, if you get, that means that model has underestimated your risk, model is not performing good. And if there are too few exceptions, then it can also be possible that model is too conservative and overestimating your risk, right? So don't think that if you have too few exceptions it is very good. No, too few exception is also bad, because you might be overestimating risk and you might be very conservative. Okay, now what is the purpose of backtesting, right? What is the purpose of backtesting? See, the purpose of backtesting is to confirm whether the model is properly calibrated or not. You also try to detect if the assumptions need a kind of revisions. Assumptions for what? Assumptions for your volatility, assumptions for your distribution. And there is definitely a regulatory use. It ensures banks internal models don't understate your risk, right? And then there is something called your Basel committee and Basel rules. See, Basel allows banks to use your internal VAR models, internal VaR models, right? Only if they pass your backtesting. If a bank records more than 4 exceptions in 250 trading days, right, then it has not passed, right? If you are exceeding 4 exceptions in 250 trading days, it's bad, right? You have broken that 1% threshold. It must hold extra capital as a penalty under your Basel traffic light framework. Okay, so overall the whole idea here is that you need to do backtesting so that you ensure, you portray, you symbol, you depict that you are a good bank, you are following all the regulation. Backtesting is about comparing your model versus your actual losses. You are looking at your exception. If your actual loss is greater than your predicted VaR, then you are getting your exception. And if your exception, generally, which is 1%, which is 2.5 days in 250 trading days, right? Or 5% means 12.5 days, or 12 to 13 days in 250 trading days. So that you need to keep in mind. If you are getting too many exceptions or too less exceptions, both are bad. And we need to understand that if you are breaching your limit, if you are having more than 4 exceptions in 250 trading days, means you are breaching the 1% threshold which has been established. You need to hold more capital, because there is a penalty which has been put by the regulator. Okay, so keep that in mind. Again, very theoretical, very easy to understand. Just understand it. Okay. All right, let's do the question, guys. In a backtesting, a VaR model that was constructed using a 97.5% confidence level over 252 trading days, how many exceptions are forecasted? Right. So see, we are using 97.5% trading days. Right. Ultimately, what are you getting? Right. So you do what? 1 minus 0.975. You get what? 0.025, and 0.025 is the day you multiply with your 252, which is 6.3. So if you get more than 6.3 exceptions, right, that is bad for you, right? So how many exceptions are forecasted? 6.3, right? Very easy. So if the model is correctly calibrated at 97.5% confidence level, you should expect around 6 exceptions in 252 trading days. If you get far more, your model is understating your risk. If you get far fewer, it is too conservative. Backtesting checks how often the VaR model is kind of wrong. This expected number of exceptions, which is 1 minus confidence level into your number of observations, right, is a very accurate and famous method to calculate your exceptions. Okay, remember that it's very easy, not very difficult at all. Okay, that's it, guys. That's how it has been done. All right, let's move to the next part. Next part is difficulties in backtesting a VaR model. Okay, when we talk about your difficulties in backtesting a VaR model, what exactly do we mean, right? See, the point here is that when you think about difficulties in backtesting a VaR model, the idea here is that backtesting sounds very simple in theory, because in theory, what are you saying? You're saying that you're comparing your predicted VaR with your actual losses. But when you go in the real life, guys, it's not that easy. Why it is not that easy? Because there are several practical issues that come, right? So what are the practical issues that come? First of all, the practical issues is that there is a portfolio mismatch. What do you mean by portfolio mismatch? See, VaR assumes the portfolio stays consistent during the holding period. Let's say the holding period is 1 day or 10 days, whatever. But in reality, what happens? Traders will buy, traders will sell, and traders will rebalance continuously. So the portfolio composition kind of changes every day. This makes backtesting harder, because actual returns are no longer for the same portfolio that the VaR was computed for, right? So it's a problem, right? Now you will say, sir, if it's a problem, how do you resolve it? See, there are ways to resolve it. You use your shorter holding periods like 1 day, so portfolio changes are minimal. So that is one way to kind of solve it. Then what are the other issues in your backtesting of our model? Second is your excluded factors. When I say excluded factor, what do I mean? What it means that VaR models often ignore your real world elements. What do you mean by real world elements? Your intraday price move, your transaction cost, your bid ask spread, your interest, dividend income, and fees, right? So you include those real world elements. You ignore those real world elements that affect your profit and loss. This causes a difference between model predicted loss and actual realized loss. And there are some sample limitation. Backtesting is done on finite historical data, let's say 250 trading days. This is not just one sample. It may not be a kind of perfectly represent the true underlying distribution of your losses. So even if you have a, let's say, a perfect model, it can show more or the fewer variation just due to your random variation, right? And then there's a need for threshold. What do you mean by need for threshold? Need for threshold means that we need a benchmark. Okay, benchmark means like 99% VaR, etc., to decide how many exceptions are acceptable. Okay, setting these threshold, if you are setting these threshold too strictly or you are setting these threshold too loosely, that affect whether the model is rejected or not. You need to understand a two-track approach. What do you mean by two-track approach, guys? Two-track approach means to deal with your portfolio mismatches, banks use two types of return. What are the two types of return? One is your actual returns, one is your hypothetical returns, right? What are your actual returns? Actual returns are returns which are including your all market and trading effect. That is actual return. Now, what are hypothetical return? Hypothetical return means assuming no trading and the portfolio held constant, right? Then we have the clean returns. What is the clean return? Clean return means these are adjusted actual returns. They remove your non-market effects like your fees, your interest, your intraday noise, and clean returns make it easier to compare with your VaR model output, right? Overall, the best practice here, which everybody should understand, is that backtest both actual and hypothetical returns. If hypothetical returns or hypothetical results fail, problem is with the VaR model. If actual kind of your results fail, the problem could be with your trading or execution, not necessarily the VaR model, right? So it's a very interesting part that you need to backtest both your actual and hypothetical return, and you need to adjust VaR if hypothetical returns fail backtesting, because if actual results fail, that means it's more of a problem with the execution, not with the model, right? Overall, the crux of this slide is that there are certain difficulties in backtesting of our model, like your portfolio mismatch, your uh, excluded factors. Portfolio mismatch causes portfolio changes daily. Excluded factors, real world profit and loss is not equal to your model profit and loss. There are sample limitations. Randomness affects your results. You are using short time horizons or mitigation to minimize this effect. There's a threshold choice. You have to define acceptable exception range. There is a clean returns, which removes your noise and make results comparable. And then the best practice is to test your both actual and the hypothetical returns. Okay, remember that. Okay, all right, so this is done. Any doubt, guys? Please keep asking. Okay, i'll I'll keep on moving ahead. Okay, if you don't ask, right, you please ask your question, right? Otherwise, how will I realize that you guys are understanding or not? Okay, all right. Next is using failure rates in model verification, right? Very interesting, guys. Very, very interesting. See, now that we know what causes the problem, right? Because in the previous slide, we understood now that difficulties in the previous slide, what was it? Difficulties in back testing a VaR model. So now that we have understood your difficulties in a back testing a VaR model, now we are talking about, let's see how to measure performance of a VaR model using your failure rate, right? We are trying to measure the performance using failure rate. So what is the failure rate? See, failure rate is your percentage of times VaR confidence level is exceeded, computed as your n by t, right? Which is your exceptions by sample size, right? So it's the percentage of days when your actual loss is greater than VaR prediction n by t. For example, if 5 out of 250 days exceed VaR, so the thing would be 5 out of 250, which is equal to 2%, right? So this is your failure rate. Okay. Then what about the Basel requirement in this case? See, banks use 99% VaR. We all know that. Then we also understand when you're using 99% VaR, then the expected failure rate is 1%, which is 2 to 3 exceptions in 250 days. Now, if you have too many exceptions here, model rejected or recalibrated, right, that we need to remember. Okay. Then there is something called probability of exception. When you say probability of exception, it is calculated 1 minus the confidence level. So I don't think that is too difficult to understand. And then there is something called your unbiased measure, right? So in your unbiased measure, basically it is the probability of exception approaches the confidence level as the sample size increases, right? So that also we understand that probability of exception increases, approaches the confidence level as the sample size increases. Next point is your model calibration testing. So the whole idea here is to statistically test if the observed number of exception, listen to me again, to statistically test if the observed number of exception is acceptable or not, right? What do? You calculate Z score using formula X, right, which is number of observation, and the formula is Z is equal to X minus PT divided by P1 minus PT, right? So Z is basically your greater than your critical value 1.96 for 95%, reject the model, right? So here the thing is, compare Z score to critical value, right? Z if your Z is greater than your 1.96 for 95%, right, you reject the model. And if Z is less than, and I'm talking about the absolute value, Z is less than your equal to 1.96, right, model performs fine. Okay. Then you look at the decision rule. You compare, you calculate Z to the critical value, the testing or the confidence level, like 95% is different from the VaR confidence, like your 99%. You look at the VaR confidence, which is used in your model prediction, right? You have your test confidence, right? Where you use to check accuracy of that prediction. So understand that as well. So VaR confidence is what? VaR confidence, right, is used in model prediction, right? Then you have something called test confidence. What is test confidence? Used to check accuracy of that prediction. Okay. All right. So the overall idea here is that you have a decision rule. Compare your calculated Z to the critical value. The testing confidence level, which is like 95% confidence level, is different from the VaR confidence, let's say like 99%. You have VaR confidence, which is used for model prediction. You have your test confidence, which is used to check the accuracy of that prediction. Overall, there is a evaluation goal, right? Right? Evaluation goal. When I say evaluation goal, you check if your observed exceptions fall inside the expected range for a correctly calibrated model or not. If yes, model is good. If no, it needs to be recalibrated. The assumptions need to be relooked at. Distribution needs to be relooked at. Overall, please understand in this slide, we are focusing on your failure rate, which is percentage of times VaR is exceeded. Then the Basel requirement, please understand that 99% confidence, 1% expected exceptions. Then the exception probability is your P is equal to 1 minus C exception probability, which is this. Then we have Z test. Z test whether actual exceptions is equal to your expected or not. Then we have decision rule, compare Z to 1.96 for 95% test, and goal is to validate the model calibration, right? Overall, please understand back testing checks how many times the VaR fails, while failure rate testing, Z test checks if the failure rate is statistically acceptable or not, right? So let me write it down maybe in the next slide, right? I'll write it down here. Please understand this very critically. Back testing checks what? How many times VaR fails, right? failure rate testing, which is Z test, checks if that failure count is statistically acceptable or not. Okay. Let's see the model verification example. Very interesting example. So here we are testing whether your VaR model is correctly calibrated or not, right? Why are we doing it? Because we need to understand whether the number of exceptions, which are the actual losses exceeding your VaR, matches with what you would expect statistically. Okay. So what is told in the question? We are told that VaR is at a 95% confidence level, and there are 252 trading days. Then actual, daily revenue fell below a predetermined VaR level at 22 days. So it's very high, right? So the question is the sample unbiased, right? So what do you mean by this question? Is the sample unbiased, right? When somebody asks you is the sample unbiased, so ultimately we want to understand here, does the number of exceptions match what we would expect? So we are asking, does the number of exceptions match what would expect? So what do you do here? You recall the z-test formula, which is x minus pt divided by under root p 1 minus pt, right? We put the numbers, 22 minus x is 22, minus p was 0.05, 5%, 252 day trading days, and we put it. The answer come out at 2.72, right? Now, when I get 2.72, right, what does it mean? Let's try to interpret the result. The critical value, right? The critical Z value at the 95% confidence, because we have taken 95% confidence level, is what? Is plus minus 1.96, right? So our computed statistic, which is 2.72, is larger than your 1.96, which is critical value, right? So if it is larger, right, we reject the null hypothesis, right? So if we reject null hypothesis. Why? Because 2.72 is greater than 1.96, right? So the model, right? So what was the null hypothesis, right? The null hypothesis here was that model is biased, right? So in case we would reject the null hypothesis that the VaR model is unbiased and conclude that the maximum number of exception has been exceeded, right? So we reject the null hypothesis that the VaR model is unbiased. So null hypothesis was VaR model was unbiased. See, we have to prove something biased now, so we'll always take null as unbiased, right? So the model is, we kind of, what do you reject the null hypothesis that the VaR model is unbiased, right? And once we do that, we conclude that the maximum number of exceptions has been exceeded. Overall, what you can see from this question here is that the confidence level is given to you 95%, which gives you p is equal to 0.05. The expected exceptions are given as your 0.05 into 252, right? 0.05 into 252, which is your expected exceptions, 0.05 into 252. So your expected exceptions were 12.6. Actual exceptions or observed exception came out 22. Z value came out as 2.72. Z is 2.72 greater than 1.96. You reject your H naught, right? What are we getting here is that when your expected exceptions are higher, means you are underestimating the risk, because your model is underestimating, because exceptions are coming more, right? So you are underestimating the risk. Okay, again, very easy question, try to understand it. Okay, moving on, guys. Next question. In the next question, a risk manager is back testing a sample at the 95% confidence level. Fine. To see if a VAR model needs to be recalibrated. He is using 252 daily returns for the sample and discovered 17 exceptions. Right. What is the Z score for the sample when conducting your VAR model verification? Right. Again, formula is same. Z is equal to X minus PT under root P1 minus P, right, into T, right? So if X is given to you, X is 17. P is given to you, which is 0.05. T is given to you, which is 252, right? T is given to you, which is 252, right? And your P is given to you, which is 0.05, right? And which is given to your 1 minus P is what? 0.95, right? And you multiply with T, which is 252, right? And you take the under root of this, right? Again, I put all the values. You solve it. A simple way to do it, that when you solve it, you get the value as equal to 1.27, right? 1.27 is the value, and ultimately what you understand here is that you calculate this with critical value, right? So critical value is what? 95% is your 1.96, right? If the critical value is 1.96, right? Therefore, what do? You are lesser than, right? It's not higher. So you reject when your value, right? When 1.27 is greater than your critical value. You do not reject, right? Which 1.27 is less than your critical value. Critical value is what? 1.96 now. So 1.27 is lesser than, right? So do not reject, right? Do not reject. Therefore, we do not reject the null, right? The model appears well calibrated. So we say that what was null? Null was model was unbiased. So we do not reject it. So we accepted it, right? So model one bad. So we are saying that, right? The model appears well calibrated. The exceptions are within the statistically expected range. So overall, what are we getting? Your confidence level, if you look at this question, confidence level 95%. Your P is equal to 0.05. Your T is equal to 252. Your expected exceptions, EE, I'm writing 12.6. Your observed exceptions, 17. Right, Z score we calculated 1.27. Decision, your 1.27, right, less than 1.96. So model is okay. Okay. All right. So we have solved two questions where you have seen that when the Z score was 2.72, we kind of rejected the model. But when Z score came out 1.27, we kind of accepted the model, right? So please understand, by calculating your Z score with the critical value, we can make a judgment whether you want to accept or whether you want to reject the model. Okay. All right, guys. Let's move ahead. Okay. In the next part, right? In the next part, we have, okay, this is what the solution is, right? We have done it. Okay, next question. Which of the following statements regarding verification of a VAR model by examining its failure rate is false, right? Which of the statement is false, guys? See, the whole idea here is that we are seeing your four statements. Let's see the statement one by one. The first statement is the frequency of exception can be determined with the confidence level used for the model, right? See, that's true. If your VAR model has a 99% confidence level, it means you expect exceptions or your losses exceeding your VAR only 1% of the time. So, yes, the confidence level directly determines your expected exceptions frequency, right? So, this statement is correct. Next is option B. According to QPEC 1995, we should reject the hypothesis that the model is correct if the log likelihood ratio LR is greater than 3.84. See, we haven't studied QPEX proportion of failure, which is POF test, but just want to add here your QPEX, your proportion of failure test, right, of log likelihood compares your observed, compare your observed versus your compares your observed versus your expected exceptions. Compare your observed versus your expected exceptions, and if your likelihood ratio LR, if your likelihood ratio LR is greater than 3.84 at your 5% your significance level, we reject null, right? Right? We acknowledge that the model is accurate. Okay, remember this, guys. So according to QPEX 1995, we should reject the null hypothesis that the model is correct if the log likelihood ratio greater than your 3.84, right? So this statement is also correct, right? This is what it is given. So these two statements are both correct. Third statement, we're looking for false statement, guys. Backtesting VaR models with a higher probability of exceptions is difficult because the number of exceptions is not high enough to provide meaningful information. Again, this statement looks little bad. Why? Because in reality, backtesting VaR models with a lower probability, right? Not at the higher probability, with a lower probability. Backtesting VaR with a lower probability, not a higher probability, lower probability, right? Of exceptions, for example, let's say 99% VaR, like 1% exception, is difficult because these are too few exceptions to draw your strong conclusions. So when exceptions are kind of rare, statistical tests have less power, right? So it is saying that backtesting models with a higher probability of exception is difficult. No, backtesting VaR model with a lower probability of exceptions, right? 1% exception, lower probability of exception. So lower would have been the right. We're not talking about higher probability of confidence level. We're talking about higher probability of exception, right? So higher probability of exception is wrong. Higher probability of exception is good. We are getting good data. That is good. When we are getting lower probability of exceptions, 1%, that is not enough. That is not enough. Lower probability is not enough. What I'm trying to put is lower probability is not enough. Right? Lower probability is not enough. Okay. Next is the range for the number of exception must strike a balance between the chances of rejecting an accurate model type 1 error and the chance of failing to reject an inaccurate model type 2, right? We have not studied this, but this is also a true statement, guys, right? The whole idea, C is the answer. The point here is that when we have your back testing, right? That's exactly the goal of backtesting, to choose an acceptable range of exceptions that balances both kind of risk, which is type 1, which is rejecting the model, type 2, which is your accepting a bad one. And this is what we learned in FRM part 1 also. FRM part 1 we studied that we need to balance out your type 1 risk and type 2 risk. So that is a fundamental principle in your finance, right? You have to always balance it out, right? So backtesting VaR models with a lower probability of exception is difficult because the number of exceptions is not high enough to provide you meaningful information. That is why C is the answer, right? Exception frequency 1 minus confidence level is true. Option A is true. Option B, cubic test rejects if LR is greater than 3.84. That is also true. C is wrong. Higher probability is difficult. That is wrong. D is right. Mentions balance between type 1 and type 2 error. That is correct. So please understand, your back testing becomes harder when you use very high confidence level like 99, 99.9, because you get too few exceptions to reliably test the model. Okay, so understand that. Now we go into your next part, which is your, so this is done, type 1 and type 2 error. Okay, when we go into your type 1 and type 2 error, we must understand that what are we doing? right? See, the whole objective of studying type 1 and type 2 error is when we backtest a VaR model, we are essentially performing a hypothesis test, right? Hypothesis test is what? We have a null hypothesis and an alternate hypothesis. Null hypothesis is the VaR model. Null hypothesis is H naught, that VaR model is accurate. What is HA, alternate hypothesis? You studied in FRM part 1. VaR model is not accurate. Okay, so VaR model is accurate, VaR model is not accurate. Okay, so we have that thing. Okay, so when we kind of backtest a VaR model, we essentially perform a hypothesis test. Null hypothesis, the VaR model is accurate. Alternate hypothesis, VaR model is not accurate. But because we test using samples, which is finite data, there is uncertainty, so we can never be 100% sure. We can only estimate probabilities of being right or wrong. There is uncertainty in your testing if you don't have infinite data, so we don't know whether certainty your model is truly accurate or not. What we can check is whether the observed number of exceptions fits within the statistical range expected for the chosen confidence level, right? So there is obviously a trade-off, right? There is obviously a trade-off you need to understand. There are two kinds of mistake which happen when you type 1 error. Type 1 error is that you are rejecting an accurate model, right? You say that the VaR model is bad when it is actually correct. Type 2 error is your beta, type 1 error is alpha, so type 2 error is you're failing to reject an inaccurate model. Means you keep using a bad model, that kind of underestimate your risk. And there are definitely trade-offs, right? Trade-off when we talk about, you can't minimize both at the same time. Tightening one, right, less tolerance for exception usually increases the other, and that is the goal of your backtesting, right? The goal of backtesting is build a VaR model, right? Build a VaR model that has low type 1 error, right, and test for very few type 2 error rate, right? So that is the whole objective, that test enough to detect when it really falls low type 2 error and low type 1 error. In short, the best model is one that is not too lenient, missing bad models, and not too strict, rejecting your good model, right? Then we have something called a binomial distribution. Binomial distribution is number of exceptions which follow a binomial distribution, right? You establish acceptable exception range at different confidence level based on the sample size. From this distribution, we can define your acceptable ranges of exception at each confidence level. And then there are certain Basel requirements, guys, that you need to know, that according to your Basel regulations, for your 99% confidence level for 250 trading days, right? If your, now confidence level 99%, we only have 1%, 250 into your 1% is 2.5 days, 2.5 exception. So Basel uses these ranges to decide if bank's model is green or yellow or red. Green is acceptable, yellow is caution, red is unacceptable. And then there is a regulatory penalty also. Regulatory penalty means if a bank is 5 or more exception in 250 days, it moves into the yellow or red zone. This triggers your higher capital requirement because it kind of indicates the models underestimate your risk. And then type 1 and type 2 error we have understood. Type 1 error rate is right tail, right? Chance of observing too many exceptions, right? Chance of observing greater exceptions from a correct 99% model, that is a right tail rejection, is type 1 error. Type 2 error is chance of observing your too few exceptions, right? Failing to reject an incorrect model, too few lesser exceptions when the left tail. So about 12.8 chances when less than 5 exceptions. So you have to determine your range. Determining range means there are two binomial probability distributions help determine what count as your normal exceptions, what count as your too many exception, what count as a too few exception for various confidence level. That's how your Basel's traffic light system for backtesting threshold also evolved, and that's what the whole objective is. So if you go ahead, you will understand that if you look at these graphs, right, you have two charts here, right? You have chart on the left side and the right side. Left side is about type 1 error, which shows exception when the model actually correct to 99%. VaR most probability masses is around 2 to 3 exceptions, but sometimes due to randomness you might get 5 exceptions also. That is type 1 error. You wrongly reject a good model. You are in the right tail of the distribution. So this is right tail, guys. This is right tail. This is your type 1, right? You are in the right tail of distribution, too many exceptions, you think the model failed when it actually didn't. Then the right chart is your type 2 error. Type 2 error is about your left tail, right? Left tail, the chart shows exception when the model is actually incorrect, right? So true coverage is only 97%, the distribution shift to the right, right? More exception expected. But if you still observe few exception, 2 to 3, wrongly conclude that the model is fine. So that's a type 2 error. Type 2 error is you failed to reject your a bad model. You failed to reject a bad model, right? And you are in the left tail. This is left tail. Okay. Too few exceptions. So overall, please understand type 1 error. If I talk, if I describe, it is rejecting a correct VaR model, right? Type 2 is accepting an incorrect VaR model. Okay. Uh, Basel rules we understand. Type 1 error is 10.8% chances, right, which is of greater than 5 exceptions, right. Type 2 is 12.8% chance of less than 5 exceptions, right, when your model is wrong, right. One is focusing on right tail, type 1 error. One is focusing on left tail, type 2 error, right. You have to balance both errors. Good model has good model, low alpha and beta. So this is alpha, right? Low alpha we want, and similarly low beta we want, right? So this is type 1 error is alpha, type 2 error is beta. I know it's confusing, guys. Overall, please understand backtesting VaR is never exact. It's probabilistic, right? Regulator expect a range of exceptions to account for your randomness. Uh, while penalizing your consistent underestimation of a risk. Your job is to ensure that your model sits comfortably in the acceptable exceptions zone. Right? That's what we want to achieve. Okay. But again, tricky, right? Just don't get confused. Okay. Moving ahead, guys. Next one is unconditional coverage. Very confusing, right? Very confusing here. Unconditional coverage is a backtesting method, right? It's a backtesting method that checks how many exceptions occurred. But please understand, it does not care about when they happen, right? So I'll repeat again. Backtesting or unconditional coverage is a backtesting method that checks how many exceptions occurred, but it does not care about when they happen. It only looks at the total count. Unconditional coverage looks at the total count of exception over the sample period. In other words, did the model produce about the right number of VaR breaches regardless of your timing? Suppose, let's say your model is 99% VaR model, expected exceptions is your 1% of trading days, which are 2.5 exceptions in 250 days. If you observe 2 to 4 exceptions, that's roughly fine. But if you use or if you see 10 exceptions, that is too many and the model is underestimating risk. If you see zero exceptions, too few, and model is overestimating a risk. So unconditional coverage checks if the exception rate matches the expected rate, right? Then there is something called QPEX test, which we saw earlier. I wrote down. QPEX proposed a statistical test to determine whether the observed number of exceptions is consistent with the expected number or not. So you studied unconditional coverage. Now you're studying similar nature QPEX 1995 test. This is called QPEX likelihood ratio test for unconditional coverage, right? Which is LRUC, right? The formula is given in front of you: 2 ln 1 minus p t minus np into right t minus n p raised to power n minus plus 2 ln 1 minus n by t, right? T minus n by tn, right? So p is the expected probability of exceptions, which is 1 minus confidence level. T is the number of observations, N is your observed number of exceptions. Overall, what do we get here, right? The whole idea here is that the first term, when we look at, right, it is the likelihood assuming the model's P is correct. The second term, right? So this is the first term is the uh, likelihood, means the probability, assuming the model's probability is correct, right? Model's expected probability of exception is correct. The second term is the likelihood assuming the observed expectation rate, which is n by t, right? So please understand, this is different, this is different. First term is likelihood. Likelihood means probability also. Likelihood assuming the model's P is correct. What is P? The probability level. So the second term. So this was the first term. First term means this was right, this one. The second term. Right, the second term. This part is different. This part is your likelihood assuming, okay, the observed your exception ratio n by t is correct. Okay. All right. Then we have the rejection criteria. Right. We compare to a critical value from the chi-square distribution. Okay. That comes from a chi-square distribution. You reject H naught. Right. You reject H naught. Right. The is rejected if the H naught is greater than 3.84. Right. 3.84 is what? 3.84 is actually 1.96 square. Right, 1.9, that's a chi-squared value, right? Chi-square 1.96 square. Okay. And conceptually, what you understand is that if it is less than 3.84, right, then if I have to write down, let me write down. If it is if just a second, guys. Okay, so if less than 3.84 means the number of your exceptions is consistent, right, with your confidence level. It means model is okay, right? If greater than 3.84, if your value is greater than 3.84, right, if your value is greater than 3.84, right, if your value is greater than 3.84, too many or too few exceptions, all right, so model rejected. Okay, so we have unconditional coverage test, we have QPEX log. Both are trying to, test the total number of exceptions. Unconditional coverage test checks whether the total number of exceptions matches the expected, the timing or clustering of exceptions. It doesn't care for. That's why it is called unconditional, because it doesn't care when the exceptions occur. and then we have QPEX test also, right? That we try to solve, right? Okay, let's go ahead, guys. Again, try to remember these final points I'm covering, right? We have a practice question now. Uh, Seems like an easy question, right? Unconditional testing. Unconditional testing does not reflect what? Timing of exceptions, right? Timing of exception. I told you, right? It doesn't care about timing of exceptions, right? It does consider the size of the portfolio, right? It does consider the number of exception, right? Depends on the confidence level. Portfolio size isn't directly relevant, but test results can scale with the sample size. Still not the main point. Timing of exception is the most important point, right? So that's important, guys. Okay. Now is you know your measuring of potential losses using VAR. Okay, measuring of potential losses using VAR. Uh, this is the last slide of your module one. Then we can take a break and then we start module two, right? So we are trying to measure your potential losses using VAR. See, VAR we understand, right? VAR. What is the purpose of VAR? VAR is designed to measure the potential loss of a portfolio. It could experience over a specific time period, gives a certain confidence level. Ultimately, we are trying to answer how much I can lose with X% confidence over the next 5 days. There are two main theories of VAR holding period. One is your when we calculate VAR, we must define the holding period, how long we assume the portfolio is held before we take corrective action. There are two schools of thought here. One is your liquidity based, another is your stability based. Liquidity based approach says that the holding period equals the time required to liquidate or your hedge the portfolio before you take the corrective action, right? So what you try to say is that it depends on your market liquidity, right? The more liquid your portfolio, the shorter your holding period can be, right? And you remember your uh, there was uh, in not here, but okay, I think you're not studied, but uh, there is a discussion of liquidity horizon also in your syllabus, right? So liquidity is very important. It depends on the market liquidity. The more liquid your portfolio, the shorter your holding period can be. And if it takes 1 day to sell a stock position without moving prices much, you must use a 1 day VAR. Next part is stability based, right? Stability based theory says in the holding period equals the time during which the portfolio remains unchanged during a non-risk perspective. Now, essentially, what you are saying is the VAR is measured assuming the portfolio isn't rebalanced or traded within that period. So if your trading desk typically hold position for 10 days before review, you must calculate a 10-day VAR, right? Now, these are two different theories, right? Both theories, which are liquidity based and stability based, usually end up giving you a similar kind of periods. In both cases, the focus is on how long the portfolio risk exposure can realistically remain constant, right? So, in your banking perspective, if you think about it, many institutions compute a daily VAR to align with the daily profit and loss reporting. This means each day the VAR is compared against that day's actual profit and loss to validate the model. So the time horizon for VAR actually 1 day for trading works must match how frequently the performance is monitored, right? Overall, the key point which I want you to take away from here is that holding period selection is more important than your confidence level selection for this application because the time horizon determines how much exposure you are measuring. A longer horizon means potential losses can compound for or grow. A shorter horizon means you can react faster with the less risk accumulation. If you change the confidence level slightly, let's say from 95 to 99%, it won't affect your result that drastically as changing the holding period. So please keep in mind holding period is very important, even much more important than your understanding of your confidence level. Very important, guys. A lot of people don't understand this, right? But this is very important, more significant than your confidence level, right? So overall, please keep in mind that uh, objective of studying this potential loss over a time horizon at the chosen confidence level. So liquidity based or stability based. Liquidity based is holding periods is the time amount or needed to liquidate to hedge or hedge position. Theory two, which is your stability based, which is holding period time portfolio remains unchanged. And common perspective is daily VAR used to match your daily profit and loss requirement. Holding period choice impacts VAR more than your confidence level, right? So keep that in mind. If you take daily VaR, it might be 10 million. If you take 10-day VaR, it might be 31.6 million. So simply extending the holding period can triple the estimated risk. That's why it is most critical assumption in your VaR measurement. Okay, so remember that overall, when you are measuring your potential losses using your VaR, your holding period assumption is what defines how realistic, how useful your risk measure will be. Confidence level matters. I'm not denying that, but not as much as the time horizon, alignment with your portfolio liquidity and trading frequency. That is more kind of alignment here. Okay, remember that. Okay, so longish kind of module, guys. So we stop here. We take a 7:41. We take a 9 minutes break, guys. 7:50, and then we come back and talk about the next part, which is your conditional coverage and Basel backtesting rule. Right, not very long, it's smaller, so we'll be able to finish by our stipulated time of 8:30. Right. So let's take a 10 minutes break and come back. Okay. All right, guys. Thank you. All right, guys. Not much is left now. Small part of the chapter is left. This is the module 2. We have done the harder part. So now it's easy part. We'll finish in 15-20 minutes, right? So this part basically now we are getting into conditional conditional coverage, right? Conditional coverage and Basel backtesting rules, right? So when you talk about conditional coverage and Basel backtesting rule, basically this builds directly on what we just learned, right? We learned what? Unconditional coverage, right? So unconditional coverage was what? We were not bothered about the timing of the exceptions. We were bothered only about the number of the exceptions, right? Now we are getting into conditional coverage, conditional, which is very different from your unconditional. So the overview here is the concept is that earlier we studied unconditional coverage. What was unconditional coverage checking? Unconditional coverage was checking does the total number of exceptions match what we accept what we expect from the confidence level. This exception and expectations keep on getting confused, right? So does the total number of exceptions match what we expect from the confidence level? Now we go to your conditional coverage. Conditional coverage, we go one step ahead. What we say here is, are these exceptions occurring randomly over time, or are they kind of clustered together, right? So time is a factor which was not considered in your unconditional coverage. Time as a factor is being considered in your conditional coverage. So conditional coverage doesn't just count how many exceptions occurred, it also checks when they occurred, what time they occurred, their timing and your independence. Okay. So it's very different from your unconditional coverage. Okay. Next question which comes to mind is that why do we need conditional coverage, right? Life was very good now when we studied unconditional coverage, everything was fine. Why we have to make our life difficult? Why do we have to study your conditional coverage? See, the whole idea here is unconditional coverage has a limitation. What limitation? Unconditional coverage ignores the time pattern, right? That is why we need a conditional coverage which was developed to capture this missing element, right? So conditional coverage or the unconditional coverage only counted your exceptions. It focused only on the number of breaches, say let's say 5 in a year, but not when they happen. If all 5, let's say, occur in 1 week, the model could be seriously wrong. But in that sense, unconditional coverage wouldn't be able to catch that, right? It is not able to catch the conditional kind of thing, right? Conditional. So conditional coverage included that time variation. It examined whether the exceptions are randomly distributed over time or whether they were clustered. Okay. So in a good VaR model, please understand, in a good VaR model, exception should be independent, not your serially correlated. That means one exception should make another one more likely soon after, right? That should not happen. One exception should not make other one more likely soon after. When you look at your clustering or bunching of exceptions, if exceptions kind of come in your clusters, right? If exceptions, let me move. If exceptions kind of come in clusters, several consecutive days, or war breaches. It might signal a regime shift. It might signal a market stress. It might signal that the model volatility estimate is too low. So it can also mean positions change or the model failed to update fast enough to the new condition, right? So when exceptions are not independent, right? If exceptions are serially dependent, means one leads to another, the model underestimate your risk during the high volatility periods. And in such cases, the risk manager should adopt models that capture your time varying volatility. What are the time varying volatility models we studied in FRM part 1? That were the models like your Garch models, right? So the purpose here to understand your conditional coverage is conditional coverage helps you determine if the exceptions are random or if the exception are caused by your model deficiencies or your trading changes, right? So please understand holistically here that unconditional coverage is all about your total number of exception. Conditional coverage also capture the number as well as the timing of exception, right? And then in this part we also have something called your Christopherson's test, right? Christopherson's test is also there, which is I think given in the next slide. Yeah, Christopherson's test. So we have also have a Christopherson's test. Okay, in your Christopherson's test, okay, we also have a Christopherson's test. So in this Christopherson's test, what is given? The Christopherson test. Now this is the statistical test used for conditional coverage, right? Who developed it? It was developed by your uh, Philip. No, not Philip. Peter Christopherson in your 1998, right? So it was developed by Peter Christopherson 1998. What did he do? Christopherson, what he did was he extended the QPEX test, which was developed in 1995, by adding a second part. What did he do? He added a test for independence of exceptions over time. So he designed two components. One was your LRUC, right, which was LRUC, which was likelihood ratio for unconditional coverage, which was your QPEX test. Then he added LRIND, right, which is LR independence, likelihood ratio for independence, which was a new part. This second part was the new addition. Okay. Then he combined them into one overall test, which is LRCC is equal to LRUC plus LRIND. And how it works is that each part LRUC and LRIND follows the chi-square distribution with 1 degree of freedom. So the component or the combined test LRCC follows the chi-square distribution with your 2 degrees of freedom, right? And interpretation here is that LRUC checks if the number of exceptions matches your expectation. LRIND checks if the exceptions are independent or clustered. So you have two factors. One is checking if the number of exceptions match the expectation, which is as the work as unconditional. When you're checking if the exceptions are independent, not clustered, which is as your conditional. So combine them together, you are getting a conditional coverage. Please understand in your unconditional coverage, LRUC was greater than 3.84. You were rejecting too many or too few exceptions. When you are looking at your independence, right, then again you are having your LRIND. So please understand when you are taking LRUC greater than 3.84, right, reject. In LRC, right, in your LRIND, if greater than 3.84, you reject. If at LRCC greater than 5.99, right, number is 5.99 LRCC. 5.99, right? This is your conditional coverage, guys. So if it is 5 greater than 5.99, model fails both coverage and independence tests, right? When you're taking individually LRUC and IND, then the value is 3.84. When you're taking LRCC, the value is 95.99. When you're doing LRUC greater than 3.84 means too many or too few exceptions. When you're taking for LRIND greater than 3.84 means exceptions are not independent or clustered. Overall, the key insight here is that if model fails the conditional coverage test CC 5.99, it means either there are too many or too few exceptions, or either they are not spread randomly clustered, or there is both, right? So either one of them too few exceptions, or they are not spread randomly clustered, one of them or either both of them. This signals a poor VaR model. It is not adapted properly to changing market volatility. Overall, please understand very clearly that unconditional coverage, we have QPEX test, which checks correct number of exceptions and you reject if LRUC is greater than 3.84. Degrees of freedom of that one is your 1. If you take your independence test, it is your Christopherson's independence test. Here you are checking exceptions are random or not. It is given by LRIND. It should value should be greater than 3.84. Chi-squared degree of freedom is 1. Right. If you take your conditional coverage, it is Christopherson's conditional coverage test. Right. So Christopherson has two tests. One is Christopherson's independence test, which is only for this part, right? One is Christopherson's conditional coverage test, which is for both, right? Here you are not only testing your number, but you're testing your timing also, and you're testing it jointly. The value LRCC should be greater than 5.99, and the degrees of freedom here is 2, right? You understand that you have a LRIND test, LRCC test, both kind of tests. Okay, remember that, guys. Okay. All right. So overall, before we move ahead, please understand unconditional coverage is about how many, kind of breakdowns or exceptions that are occurring in a year. Conditional coverage is, did they occur randomly or all in a week, right? If it all happen together, there is a systemic issue. Overall, please understand that when you look at your conditional coverage, it's a more advanced test of your VaR accuracy. It combines how many exceptions occurred and when they occurred, making it a better indicator of whether your VaR model correctly captures your time varying risk or not. Okay. Next part is, the last part is in your syllabus in this chapter is your Basel committee rules for backtesting that we need to understand. Focus here, guys. The whole idea here is that the Basel Committee, which is the global banking regulator, created rules for backtesting. Why? Because they wanted to make sure banks' internal VaR models are reliable, banks' internal VaR models are statistically sound, banks' internal VaR model are appropriately penalized if they understate their risk. So reliable, statistically sound, penalized. So this kind of last conditions, right, connects your statistical VaR test to your regulatory capital requirement. The core idea here is you balance your type 1 and type 2 error, right? So backtesting tries to find that middle ground between type 1 error, which is rejecting a good model. Good model is you're too strict. Type 2 error is accepting a bad model which is too lenient, right? Basel rules are designed to make sure that your banks don't deliberately use a faulty model that underestimate your risk, which is type 2 error, while also not punishing them too harshly for random bad luck, right? So what are the requirements for the Basel backtesting? Requirements are your confidence level, right? Banks must calculate VaR at your 99% confidence. This is stricter than your typical 95% VaR used in internal risk analysis. Then you look at the backtesting period. VaR must be tested over the past year, which is 250 trading days, right? Then there is a expected exceptions and 99% confidence. The expected failure rate is 1%. So the expected exceptions per year, you calculate 250 into 0.01, which is 2.5 exceptions per year. Meaning, in a good model, you should roughly see 2 to 3 exceptions, VaR breaches per year. And then they made a Basel penalty zone. What is the Basel penalty zone? If the number of exceptions is too high, let's say Basel assumes your model is underestimating your risk and it increases your capital requirement as a penalty. This is done using a capital multiplier K, right? So what is the penalty design here? Each bank's VaR is multiplied by capital multiplier K. The default multiplier starts at 3. If the bank's backtesting shows too many exceptions, the multiplier increases step by step, meaning you require more capital to be held, right? So if your exceptions are, let's say, between 0 and 4, right, that means it is a good zone, it's a green zone, right? If you are between 0 and 4, it's a green zone. The capital multiplier is 3 in that case. So you are in a kind of a safe place. Model is reliable, no penalty, etc. Right? This is a default multiplier. Now, when you are in a yellow zone, which is 5 to 9, right, you see yourself that how the value is 3.4, 3.5, 3.65, 75, 85, right? Model might be inaccurate. There is a model penalty, minor penalty, which keep on increasing. And then there is a red zone, which is 10 or more, which is multiplier is 4. Model is unreliable, and there is a major penalty. So in case somebody gives you 3 exceptions, that is green zone. Multiplier will be 3, no problem. If you have 6 exceptions, it will be yellow zone. Your K will be your 3.50 in 6. Right? Moderate penalty, if you have 10 plus exceptions, it's red zone, K is equal to 4. Serious penalty, model likely rejected. Right? So this is rejection, guys. Rejection of model. Likely. Okay. The higher number of exceptions, the higher the penalty. This kind of discourages the banks from using your VaR models that understate your true market risk. A higher K, right, means the bank must hold more capital, lowering return on equity. So banks are motivated to maintain your accurate and conservative VaR models. And let's look at the next slide. I think there's a question. Okay, so in the Basel Committee established 4 categories for causes for exception, which are the following does not apply to one of those categories, right? So when you look at the categories, sample is small, intraday trading activity, model accuracy need improvement, the basic integrity of the model is lacking. See, you look at these things. The first option is sample is small. According to the Basel Committee, exceptions, VaR breaches can be caused by 4 main reasons. So 4 main reasons are your bad luck, right? Okay. Your second is intraday trading activity. Third is model accuracy issues. Fourth is okay. So according to Basel Committee, VaR breaches can be caused by 4 main reasons. Right. This is given by your Basel Committee, guys. Right. Okay. So you see yourself, right? Sample small is not there, right? Does not apply, right? Does not apply to one of those categories. Right. So A is the answer. Remember this, guys. I think this will not discuss. So overall perspective here is that small sample is not one of the official Basel causes, and rest all given. Remember, if you ensure your discipline through your penalty zone, Committee wants that. Balance your type 1 and type 2 error, reward good models, lower capital requirement, penalize the bad model with higher capital multipliers. Right? So that's the whole thing. That's complete our chapter. I think we have gone in a lot of detail. I think I should give you a table here. I think I was thinking, I was worried about whether time is enough or not. I should give you a table here because I think that will add more value, make you a table kind of that will give you. I think this slide has space. So I just want to add a few things here, right? So the whole idea is, but I can make a slide here in between. Just want to give a summary kind of this thing because conditional coverage and this creates a problem. So I just want to put idea that concept test. Concept is your unconditional coverage. Test is your Quebec test. Concept is your independence test. Test is your Christopherson's independence test. Then is concept is your conditional coverage, which is Christopherson's conditional coverage test. Right? Then what it checks? What does this test checks? Okay. This checks your correct number of exceptions. Right? This checks if exceptions are random. Random means there is a pattern or not. This checks your number plus timing. So this is timing only jointly. Okay. You reject. When do you reject this test? Reject the null hypothesis. Right. You reject the test when LR UC greater than 3.84. You reject LR IND independence when greater than 3.84. You reject LR conditional coverage if greater than 5.99. Joint test, the number is 5.99. Right? If you think about degrees of freedom, it is 1, 1, 2. Right? What is your null here? Null is, right, model is unbiased. Means good. Right? If you reject null, right, means model is bad. If you fail to reject null, FTR null means model is good. Right? HA is model is biased. Reject null means accepted alternate. Model is bad, comma biased. Right. So I just wanted to give you the summary because I think this summary is very helpful if you are studying for the exam. Right. This gives you a perspective to remember. I think the rest is all easy. I think anything else, I'm just checking my personal notes. If I have skipped anything, uh, I don't think we've covered everything else in quite detail. This was before stability and liquidity theory, right? Remember this definition, right? What happens? Common practice requirement, objective, right? More important than your confidence level, right? So this is the theory. I don't think there is an issue here. Timing of exceptions I covered. This QPEX text is very, very important, right? It's a chi-squared value. Left tail, right tail, very, very important, right? Have an idea about your type 1 and type 2 error, because this creates lot of confusion of type 1, type 2 error. You have to have a, you know, understanding here, right? If you get, you want low alpha and low beta, right? That you want type 1 and type 2 error, you understand. Okay, here also I can add one small thing. In fact, even though it is given, but this also creates confusion. I, in my personal notes, I have made some summary here, right? I can make a small thing or note here, which will help you guys for exam, right? Just, it makes your remembering easier, nothing else. So again, these are personal notes, guys, uh, like made over many years, right? Concept here is that if you have type 1 error, right? uh, Type 1 error is what? Is rejecting a correct VaR model, right? Then you have type 2 error. Type 2 error is accepting an incorrect. The pen gets hanged here. That's why writing doesn't come good, guys. This software doesn't allow you to write so smoothly. Type 2 error, accepting an incorrect VaR model, right? So type 1 error, understand that, right? When you have, so uh, okay, then type 1 error type is error rate, right? Rate is this, I written in the previous slide also, but 10.8% chance, example, this is example, 10.8% chance 10.8% chance of greater than equal to 5 exceptions. Means here you are looking at your right tail. Here example of rate is your 12.8% chance of less than 5 exceptions. Here you are looking at left tail. This is your left tail. This is your right tail. Right. So have an idea. Right. Okay. So in your type 1 error, right, let me write above. Type 1 error, let's say you are getting your observed is 6, expected were 2. That is type 1 error. Okay. Here your observed 2, right? Right. And though, right, model underestimates risk. Okay. Right tail, left tail, I told you. Good model, I told you. Low alpha. Alpha is this. Low beta. Low alpha, low beta. Right? You have to maintain a balance. Generally, you focus on getting low beta, but overall low alpha, low beta, right? So that's what we have. I think this is also done. Then I don't think there is anything else. We need to type an error, rejecting an accurate model. Oh, okay. One more thing I want to write here, one line more. So type 1 error, you say, right? The VaR model is bad. When it's actually correct. What is type 2 error? Type 2 error is you keep using bad model that kind of underestimates your risk. Okay, so these are the confusing points I wanted to add, guys. This is for type 2 error, this is for type 1, right? This is for type 1, right? I just want to add because what happened in exam is they'll give you some confusing language you might miss out, right? So just wanted to add these few points. Otherwise, I think we have done a good job. We have covered everything. Higher probability, lower probability is not enough, right? Okay, that we have covered. Z values we have calculated. We have seen that what model was unbiased, or everything we have done, right? So that's all have been covered, right? This part, I think here, uh, unbiased means null hypothesis. Unbiased means model is good. Means this part means unbiased means model is good, right? So null hypothesis means model was unbiased, means model was good. So when again same logic, you reject null means model is bad. You fail to reject null, FTR I'm writing a short form. Fail to reject null means model is okay or good. Okay. Null hypothesis, model was unbiased. So this is null hypothesis. Okay. All right, guys. So this is it, guys. Anybody any doubt can ask me, but I think we have done a phenomenal job by covering this chapter, everything with a lot of detail. Go back, revise it, try to understand it. Everything is covered, right? Everything. We got time, extra time. I have made few extra notes also for you, right? So if you just remember these final points, I think you will be totally fine, right? Totally fine. So if you have any doubt, you can ask me, right? Anyone any doubt? Were you able to understand, grasp it, or was it too difficult or okay?
Pace was actually good, but we required, I required that notes also, for revision.
Fine.
I required these notes also for revision
Okay.
purpose.
Okay. Yeah. Yeah. Definitely, you will get the notes, right? No worries. Okay.
Yeah.
All right. I'm glad you guys are liking it. That's the objective. I have made some notes. I'd go back and see it. Writing is the issue here because software hangs your pen. Otherwise, my writing is not so bad. Just want to clarify. Right? Writing comes out bad here because it doesn't allow you to write frequently. It stops in between, right? So not easy to write. Okay. All right, guys. Let's meet next week. Go back and revise. I'll upload two recordings more. Market risk 2 and 3. Those are also easy chapter. You can watch on this, weekday. Okay, week, right? All right, guys. Thank you.